Hi everyone, my name is Ashley Bedford and welcome back to the Runtime Diaries. We are on day number 3 of the hashtag 30 Days of Code challenge with Educative, and I am super excited for this problem. So, today's problem is called number of steps to reduce a binary number to 1. Now, was this challenging? Yes, but in a different way. It challenged me how to think in binary, put that mindset on. So, without further ado, let's get into it. Let's start with what we're given. We have a binary string like 1101. We can take 2 types of actions. If the number is even, divide it by 2. If it's odd, add 1. Our goal is simple. Count how many steps it takes until the number becomes 1. For example, 1101 in binary is 13 in integer format. Add 1, divide, add 1, divide until we reach 1. Easy enough on paper, but the challenge is in understanding how the steps actually work in binary. Here's where I started. And this is the version I think a lot of people would write first. I just converted the binary string into a decimal integer, then used a simple loop. Divide if even, add 1 if odd. The logic feels fine. It even passes a few test cases, but once you dig deeper, it fails others completely. And the reason is subtle here. I was thinking like a human, not like a bit system. Here's what I realized. I was thinking in integer arithmetic, not binary states. In base 10, adding 1 is straightforward. 13 plus 1 is 14. But in binary, that same operation means something completely different. Look at this sequence. 1101 goes to 1110. Which goes to 111, which goes to 11, then to 10, and then finally 1. Every time you add 1, you're flipping bits until you hit the first 0. That's what's called a carry. Carries move left, flipping 1s to 0s until they find a resting place. My code didn't account for that. It was simulating math, not modeling how bits actually behave. So I rebuilt it. This time, literally working with the binary bits themselves. I converted the string into an array of integers and walked through the logic step by step. If the last bit is 0 and there's no carry, pop it off. That's divide by 2. If the last bit is 1 and no carry exists, trigger a carry and count 2 steps. Keep going until the length of the array plus any active carry equals 1. It worked, but it was messy. Lots of conditions, popping elements, and using extra space. It was a great learning step though because it made me see how binary behaves. Once I stepped back, I noticed something fascinating. Carries follow a pattern. Every 1 pushes a carry left, and every 0 simply gets divided. So in other words, the carry pattern defines the rhythm of the entire operation. Think of it like dominoes. Each one knocks over the next bit until it finds a 0 that can absorb it. That's when I stopped writing code and started writing behavior. My naive approach worked, but it wasn't optimal. The time complexity was O of n, so we looped through every bit. The space complexity was also O of n, since we stored the binary string in an array copy. The logic was fine, but it relied on too many branch conditions, and I knew I could simplify it further. That's when the optimized version clicked. Instead of literally moving bits, I could walk backward through the string, analyzing each bit's relationship to the carry. Now, instead of simulating the process, I was modeling the pattern. So let's break that down. We're looping from right to left because that's how carries move. The line bit equals s of I equals 1 as a string simply checks whether the current bit is a 1 or 0 and converts it to true or false. Then the most interesting line, steps plus equals 1 plus bit XOR carry. XOR here means, are bit and carry different? If yes, we need 2 steps, one to flip, one to divide. If no, just 1 step is needed. Finally, carry or equals bit ensures the carry stays active if a 1 was seen. The loop ends, and if a carry still exists, we add 1 last step. That's the difference between simulating what happens and understanding why it happens. Both solutions here are O of n, but this one uses O of 1 space. We eliminated the extra array and just worked directly with the binary string. The real optimization here isn't about speed, it's about clarity. Now, each bit operation is direct and purposeful. You can almost see the carry moving through the string. Let's summarize what changed between the 2 versions. So we have our metric, our naive solution, and our optimized solution. So for our metric of time, both the naive and optimized solutions gave us O of n. For our space metric, naive solution was O of n, and the optimized version was O of 1. Now for our clarity metric, the naive version was a medium level clarity, but the optimized version was a very high level clarity. For our binary awareness metric, the naive version was implicit and the optimized version was explicit. And then for our micro optimizations, we didn't have any in the naive version, but we did add some to the optimized version, which are using local bindings and the XOR method. So the biggest shift here wasn't in code length, it was in mental clarity. I stopped coding line by line and started reasoning by pattern. Here are the takeaways that stuck with me. Don't simulate logic. Capture model behavior instead. Instead of following every tiny operation, learn the pattern that drives them. Binary operations have their own rhythm. Carry propagation is the real heart of this problem. XOR and bitwise operations aren't scary. They're shortcuts to expressing behavior. And most importantly, we need to debug our mental model, not just the code. When I finished this one, it hit me. The key wasn't learning how to fix my code, it was learning how to see like a computer. When you stop trying to simulate what your program does and start understanding why it behaves that way, you stop coding in Python and start thinking in bits. That's the mindset shift I'll carry into every future problem. And that's a wrap. Thank you for tuning in to day 3 of the hashtag 30 Days of Code challenge with Educative. And if you like this video, if it helped you, share it with a friend, like it, subscribe to our channel. We would love to have you for day 4 and onward. I'll catch you later.